Okay, we'll finish up the topic 6 worksheet now. We are on problem 5, and we're going to graph this function f of x by following the steps that are given here. Part A, we want to write the equations of the vertical asymptotes for f. Okay, so remember that we get the vertical asymptotes just by knowing the domain of f. Of course, I know I can't divide by 0. So just somewhere on the side, if I set the denominator equal to 0 and solve, I'm getting x equal plus or minus 1. And since I'm throwing away 1 and negative 1 from the domain, I'm going to have corresponding vertical asymptotes at x equal 1 and x equal negative 1. Part B, we want to write the equation of the horizontal asymptote. Remember, we compared the degree of the top to the degree of the bottom to get the horizontal or oblique asymptote. Whenever the degree of the top is less than the degree of the bottom, y equals 0 is always a horizontal asymptote. In this problem here, I've got a degree 1 polynomial divided by a degree 2 polynomial, and so therefore y equals 0 would be the equation of the horizontal asymptote. Part C, determine the points, if there are any, where the graph will intersect the horizontal asymptote. A graph can cross a horizontal or oblique asymptote, and that sometimes happens. Okay, so we're going to check for that here. To figure that out, we want to set the function equal to the asymptote and then solve. By the way, a function will never cross a vertical asymptote. Okay, so keep that in mind. Well, if I set the function equal to the asymptote here and solve, multiply both sides by x squared minus 1, that'll clear out the fractional form on the left. 5x equals 0, divide by 5, that means that x is 0. If x is 0, and you plug that into f, you get y equals 0. So even though we're going to have a dotted line at y equals 0, we still want to make sure that the point 0, 0 is on the graph. Part D, I want to determine the intercepts for the graph and then sketch the graph. So to get the x-intercepts, I let the function be 0 and solve. Okay, I've already done that actually, and I get x equals 0. So this point is actually an x-intercept. Of course, it's also going to be a y-intercept too, since if x is 0, y is 0, right? So here's my one and only intercept on this graph. It's right at the origin. Now, after doing all this work here, I only know one point on the graph. It is typical to need to gather up more points by using a table of numbers, just so that you have a more complete picture of what's going on. And so that's what I'm doing here at this point. Selecting values just so I can see some additional points on the graph. Plot as many points as you need. Okay, but also keep in mind that the graph has to flow with these asymptotes here. So once you have a few points in an area, you should kind of know what's going on in that area. If we get the middle section set first, of course I know 0, 0 is on the graph. If x is 1/2 and you plug that into the function right here, when x is 1/2, I was getting negative 10/3 when you simplify. So okay, here's 1/2, negative 3 1/3, that'd be about right there. There's that point that I plotted. Okay, and then if I let x be negative 1/2 and plug that into the function, I'm getting 10/3. And so okay, here's negative 1/2 10/3. I've got that point. And I've got these two boundaries here, these two vertical asymptotes from my work done earlier. And I know the graph has to flow with these boundaries. So in the middle, I think that the curve is going to be coming down the left vertical asymptote. It'll be on the right side of it. It's going to pass through these points and then approach the right vertical asymptote, but on the left side of it. Now there's a left section, a middle section, and a right section of this graph. We've got the middle section done. Let's get the right section done next. So if I continue this table here, if x is 2 and we plug that into the function. 5 times 2 is 10. We're dividing by 3, so 10 thirds would be coming out of that. Here's 2 10 thirds, that point there. And if I were to let x be 3 and plug that in, 5 times 3 is 15. I'm dividing by 8, and so 15 eighths would be my output. 15 eighths is a little bit less than 2. So at 3, I want to plot a point that is a little bit less than a height of 2. And with those 2 points being located where they are in these 2 boundaries also on the graph, the curve is going to be coming down the right vertical asymptote on the right side of it, pulling away from that slightly. It's going to go through these points and then approach the horizontal asymptote from above it. And then I'm getting the left section done, so if x is negative 2, then plug that in. 5 times negative 2 is negative 10. You'd be dividing by negative 2 squared is 4, minus 1 is 3, so I'm getting negative 10 thirds as the output. Okay, so here's negative 2, negative 3 and a third. And then I just use one more number here, like if x is negative 3, and we plug that in. 5 times negative 3 is negative 15. Negative 3 squared is 9, minus 1 is 8, and so I'm getting negative 15 eighths as the output. Negative 15 eighths is a little bit bigger than negative 2, so at negative 3 I want to be plotting a point that is just above that height of negative 2. Okay, and then with these 2 points, I would think that the curve is going to be coming along below the horizontal asymptote here in quadrant 4. It's going to be pulling away from that slightly. It's going to pass through these points and then be approaching the vertical asymptote. It's never going to get there, though. Okay. Problem 6 is just two of the equations that we had looked at in sections 4.7 and 4.8. We talked about rational equations and then radical equations. I've got an example of each one here. So here's an example of a rational equation. I want to solve for x. The first thing that you usually want to do when you have a rational equation is you want to get rid of the fractional form that's there. So I want to clear all the denominators out by multiplying by what's in common to all these denominators. X minus 2 times x plus 2, that would be the same as x squared minus 4. And so to clear out everything on both sides, let's multiply both sides by x minus 2 times x plus 2. X minus 2 times x plus 2, when you distribute that into the first term on the left, the x minus 2's will cancel. That's going to leave you with the 4 that was in the numerator there. Also, this x plus 2 is coming into the numerator there on that first term. And then make sure that you distribute into both terms here. X minus 2 times x plus 2 times 1 is x minus 2 times x plus 2. On the right, x minus 2 times x plus 2, that's the same as x squared minus 4. So I've got an x squared minus 4 in the denominator, going to cancel with an x squared minus 4 that would be up top here. That'll leave me with 16 on the right. And now notice how I no longer have fractional form on any of this, and that's good. That's what I wanted. If we get everything onto the left and then combine our like terms, we're looking at x squared plus 4x minus 12 equals 0. That's a quadratic equation, so of course the next thing would be to factor the left. X plus 6 times x minus 2 would be how the left side factors. And when you set the factors equal to 0, you get x equal negative 6 and x equal 2. Now you want to make sure that you are checking your answers when you have a rational equation. These extraneous solutions can sometimes come up. An extraneous solution is a number that it isn't actually an answer, but it came up in the calculation. Now, the only thing that we are checking for in the case of a rational equation is that we can't divide by 0. Well, 2 is a problem because that's going to create 0 down under here on both of these fractions, actually. Okay, so 2 would be an extraneous solution. I'd want to throw that away. Negative 6 is all good because we don't end up getting 0 in the denominator of either of these two fractions. So negative 6 would be the only solution, 2 would be extraneous. All right, part B, we've got a radical equation, and so we want to solve for x. The first thing that you'd want to do early on is to get rid of the radical. In the case of a square root, you want to make sure that the square root is all alone and on one side. Now we've already got that in this problem here. And so I'm ready to get rid of that square root by squaring both sides. When you square a square root, those two operations go away, and that'll leave you with the expression that was underneath the square root, which in this problem is 3x plus 7. We're squaring both sides, so on the right I'd want to make sure I FOIL out 3x plus 5 times 3x plus 5. When I FOIL, I'm getting 9x squared plus 30x plus 25. And notice how at this point I no longer have a square root going on, which is good. That puts me back on familiar ground here. If we get all the terms onto one side, then we have a quadratic. And you can make the numbers a bit nicer by dividing both sides by 9. X squared plus 3x plus 2 equals 0 is the quadratic, and that's going to factor nicely as x plus 1 times x plus 2. And when you set the factors each equal to 0 and solve, you'll get x equal negative 1 and x equal negative 2. Now, a radical equation is another kind of equation where you can sometimes have these extraneous solutions come up. So at this point, we're saying that negative 1 and negative 2 may or may not be the right answers. We don't know. We got to check and make sure. Well, if I check negative 1 by plugging that into the original here, 3 times negative 1 is negative 3, plus 7 is 4. The square root of 4 is 2. And on the right, when x is negative 1, 3 times negative 1 is negative 3, plus 5 is 2. Okay, 2 equal 2, that's a true statement. So negative 1 is going to be kept. Now check negative 2. Same deal, plug it into the original and see if you get a true statement. When I plug negative 2 into the left, 3 times negative 2 is negative 6, plus 7 is 1. The square root of 1 is 1. And then on the right, when x is negative 2, 3 times negative 2 is negative 6, plus 5 is negative 1. So you're saying that 1 equal negative 1, which of course is not true. Therefore, negative 2 would be an extraneous solution. You'd want to throw that away. So the only answer here is x equal negative 1. Okay. Be sure that you check your answers for extraneous solutions. It's common for students not to check their answers. There are only 3 kinds of equations in all of algebra where you have to check your answers. They are a rational equation, a radical equation, and then a logarithmic equation. We're going to see logarithmic equations in the next chapter here, kind of midway into the chapter. So, all right. At this point, we're now done with the Topic 6 worksheet.